So as I said at the start, you're going to be able to solve for critical velocity and solve tension problems for vertical motion as well. Okay, so consider a ball moving in a circular path as shown. So think of me with the rubber stopper again on the string, and we're going around and around in a circle. And where is the play button? There it is there. Okay, so what do the red and blue arrows represent in this situation? Just watch there. It's too bad I can't loop it, but. Red is tension, you think? Okay. Do people agree? What's happening to the value of the red? Increases at the bottom and decreases at the top? Does it go to 0 at the top? It doesn't, does it? Doesn't go to 0 at the top. And then the blue one seems to be always going down, right? Which, Joel is correct, is the direction of gravity, right? So I don't know if you, I mean, I'm going to put this down for my notes that I'm posting. Whether you guys write it down or not, it's up to you, right? But red would be the tension, and blue is gravity, right? It seems silly for you to write it down because you don't have the picture, right? You don't have the animation. What happens to the speed of the ball? Watch again and watch what happens to the speed of the ball. Speeds up on the way down? Slows down at the top? Does that make sense, sort of from your own experience type of thing? I think so, right? No? Come on, I'm sure you've done that kind of thing at least once. What happens to the tension in the string? Well, it definitely changes, right? Would you say that it lessens at the top? I think so, right? So these are all sort of intuitive things that we're going to sort of delve into mathematically here. Okay. So here is the same thing, but with a little bit more to see, right? So once again, you can see the tension there. In fact, this time the tension almost goes to 0, right? But this W, what is that? That's the weight, right? So here it says, we show a mass moving in a vertical circle with negligible air resistance. The string is massless. In other words, we don't worry how much the string weighs. Also shown is the force due to gravity on the mass and the force T exerted on the tension by the tension of the string, and the units are arbitrary. In other words, they don't matter. Notice that the speed of the mass down here, as it comes down to the bottom, it's reaching its maximum, and then as it's going up, it slows down, right? And now it's speeding up on the way down, right? And the actual value of the tension goes down to almost just under 2, 1.7. What would I do? I can change my speeder. What would I have to do to make the tension go to 0? Slow it down. I think everyone knows that, right? If I slow it down, then it goes to 0, right? But you will notice that it's still staying in that uniform, right? So in other words, this speed here, this 10 whatever meters per second, would you call that the minimum speed to keep going in the circle? Right? So how does that relate to the car video? Yes. So the physics dude figured out that it was 36 miles per hour at entry because as you slow down, when you get to the top, right, there would be some number, let's just say, I don't know, 30. He figured out that 30 was the correct speed you had to be going at the top to do what? To stay on the track, right? To still have that inertial pull out and to stay on the track, right? So then he figured out what the speed at the bottom is, 36. And of course, if I speed this up, what's going to happen to the tension? We're going to get more friends, more tension. Okay, so have I sort of given you sort of the intuitive kind of background feel for things? Let's deal with the actual math. This you should draw. I'll pause and let you get it down. What would you call that speed that you have to go to keep going in a circle? What would you call it? Okay? Question. I call it Bob. Well, minimum speed, or we actually call it the critical velocity, right? Because it's obviously to the guy in the car, it was critical, right? So because of gravity, the speed of the ball is not uniform. So while we say uniform circular motion, we sort of know that the speed is not uniform. We saw that on this previous one here, right? We saw that the speed's changing, right? So where is it fastest? At the bottom. And where is it slowest? At the top, right? The ball accelerates on the downward path and decelerates or slows down on the upward path. Speed is at a minimum at the top and a maximum at the bottom. But that's intuitive. I hope you see that. And now we're going to be dealing with, basically what we're going to do here is we're going to derive a formula. And it actually works out pretty easy. Yeah, I know. That's the usual reaction. At the top, which is where it's going the slowest. At the top, we have, so this is just this picture here, the top. I'm deriving for it. You do what you want, Carter, right? So FCT, total centripetal force, is equal to the string force, FST, string tension, plus the weight force. And would you agree that all three of those things are all down?
Yes.
Right? The centripetal force must be down, the string force is down, and the weight force is down. And the string force is, or sorry, the centripetal force is mv squared over r, and that v is the minimum. So v min squared. And that's equal to the string force plus the weight force, and they're all down. Again, this is another one of those situations where it's really not going to make sense until we get to the end. What's different about the bottom? Exactly. The weight is still down, but the tension is up. So at the bottom, here I've got, FCT, that would be FC top, sorry. Centripetal force at the top. FCB, centripetal force at the bottom. Top, bottom. Is equal to the string force at the bottom plus the weight force, right? And again, FCB, the centripetal force is mv squared, but this is the maximum speed over r is equal to FSB plus FW. This implies that there is some velocity below which the ball will not move in a circular path, and the string will slacken at the ball's highest point, right? And I've been sort of demonstrating that. Good one. Okay, so like there is some, if I go really fast, it's going to stay in a circle, but if I go slower, slower, and slower, there's some point where the string loses its tension and it falls out, right? And if you're in a car, you're going to fall. Same idea, right? This could also happen if the car did not have enough speed to make the loop tube, and here it is. Here, this is not actually what happened. Don't worry. But that's what could have happened, right? No. Just a cartoon. How risky was that maneuver that they did, do you think? Pretty risky, but they certainly, do you think they took a lot of precautions? I mean, they went and found the physics dude, right? Yeah, they probably should have done that, right? They did, but they should have actually considered, you would think that they would have actually taken the car and driven it over like where the road meets the loop-de-loop, right? Like clearly there was a, right? They'd ramped that a little bit, but there was clearly a bit of a, and it caused some problem with the bumper, right? And it could have actually slowed him down significantly, right? So I'm surprised that they didn't. You would have done it, Carter? I don't even know if I could have watched someone do it. Just watch it. I've seen that video hundreds of times, and just watching it just kind of gives me the. Anyways, okay, so the minimum value is when the string force is equal to 0, right? And at this time, the ball just makes it around the circle. So what happens to our values in our little formula thing? Well, and this should be FC top, right? I got to fix that. So Fc, the centripetal force at the top, is equal to the string force at the top plus the weight force, but the string force is 0. So I plug in a 0 for my FST. And what do you get? You get mv squared, mv min squared over r is equal to 0 plus mg. And what happens? What happens mathematically? I've got m and I've got m, right? Yeah, the m's actually cancel out. And you get v squared, v min squared over r is equal to g. The masses cancel. And if I want to write it for v min, how do I rearrange that for v min? Multiply both sides by r, and I take the square root, and you get v equals the square root of rg. This is known as the critical velocity. And if we went back to the video, you would see that formula on the professor's whiteboard. You wouldn't see it in its entirety, but you would know that that's what he's talking about. Do you remember what they said the height of that structure was?
40.
Was it 40 feet? Okay, so they would have had to convert feet. Well, they probably would have left it in feet, found the radius, right? Found this critical velocity, multiplied by g, converted it to miles per hour, and not only that, but that's the speed that it has to be going at the top, right? So they would have to work that backwards to figure out how fast you'd have to be going at the bottom, so that as you slow down, then you would still be going that. Was it 36? No, we don't know. Actually, we didn't know what the critical velocity was. We just know it's 36 down here. It's probably 30. So really, the math's not that hard, right? Well, would you want to get more than one opinion?
Yeah.
Would you want to do it more than once? Like do the math? Test it? Yeah, I think so. Don't pull a NASA. Do you guys hear what? Okay, so this value of v min is called the critical velocity. It depends only on the radius of the circle and acceleration of gravity. It does not depend upon the mass of the object in motion. So it doesn't matter how much the dude in the car or the car itself actually weighs. It does not depend upon the mass of the object. Okay? I don't know. Do you need to write that down? All you really got to know is
Mass doesn't matter.
v min is equal to the square root of rg. Is there an m in there? No? How come? Because the mass don't matter. Now, what happens if I go faster and faster and faster on a string like this? Well, no big deal. I guess unless I went so fast that the string actually broke, right? But satellite in orbit, if you've got your satellite up there that your cell phone's connected to, right? If it's in orbit, it actually moves about a planet with the critical velocity for its radius of orbit, or its altitude, right? So if it's like 400 kilometers up, they know that radius, and they know how fast the satellite has to go, so that it keeps doing what? Staying in orbit. But what happens if it goes faster? It's going to go out to Pluto. No? Oh, maybe not yet. Okay. What happens if it's not going fast enough? It crashes to the Earth, just like the first space shuttle, first space station Mir landed in the Australian outback. Well, put the phone away. Okay, so let's do a couple sample questions here. And I can't believe I don't have that. I'm doing a new number 3, but I don't have it there. That's bizarre.
That's it?
Well, we should do sample question number 3.
A 0.5 kg body moves in UCM in vertical
Yeah.
circle of radius 1.5 period of 0.5. Find 80 speed body in its orbit. B. Average centripetal
Yeah.
force needed to maintain a motion. C. String.
Okay, you have the question. Is it 0.5 kilogram body on yours?
Yes.
Okay, so the mass is 0.5. Moves in UCM. Now again, it's not a constant velocity, so that's a bit of a misnomer, but it's in a circular motion in a vertical circle of radius 1.5 meters and a period of 0.5 seconds. Find A, the speed of the body in orbit, the average centripetal force needed to maintain this motion, and the string tension when the mass at the bottom, and the string tension when the mass at the top. And I should probably add the critical velocity in there as well. I'll do some editing here. Okay, so let's go with the easy one first. What is the speed of the body in its orbit? So again, this is part A. V is equal to the circumference, 2 pi r divided by the t. 2 pi, the radius is 1.5, and the period is 0.5, and you get 18.8 meters per second. Pretty easy, really. Is that speed, does that speed remain constant? No. So this is in fact the average velocity, right? It would actually be going faster at the bottom and slower at the top. Right. Okay, so because of this average speed, in part B, it's asking you for the average centripetal force. So the average centripetal force is based on that average speed, which is relatively easy to do, mv squared over r. And again, this v here is that average that we're talking about. And I try not to clutter up my formulas with things, but I think it's important in this case here. So the mass is 0.5, average velocity 18.8 squared, and the radius 1.5. 117.8? Can we round that up to 118 just to make it easy for ourselves? Okay. We'll say 118 newtons is the average centripetal force. Now, this Fc is in fact the net force. It's the combination of, if we go back to that PowerPoint, the slides, it's the string force plus the weight force. But sometimes they work together, sometimes they work opposite, right? So this is in fact, this net force is the string force plus the weight force. And when I say plus, I mean vector addition, right? You add the string force and the weight force together, that provides the net force, or that is the net force, which is providing the centripetal force. And I have to be very careful here with what I'm doing. At the bottom, right, here's the string, the Ft here, right? At the bottom of the circle. Is the 118, what direction is it?
Yeah.
The bottom of the circle. It's up, right? Okay, so this is going to be plus 118 is equal to the string force, but the weight force is? Right, so let me write it this way, just for completeness sake. Right? So it's kind of like that idea about applied force and friction force working opposite. So because the weight force, the gravity, is acting opposite to the string force, we actually need, when I take that minus 4.9 to the other side, and then just flip them, right, I'm going to get 118 plus 4.9, which gives me 122.9, but it gives me a bigger value than the centripetal force, right? Does that make sense with our, remember that beacon, that sort of master statement that we had there was that the string tension at the bottom must be more, right? So does that make sense to that? It does. And I would urge you, when you're done a question like this, sort of just stop and think about, okay, does this make sense with what I intuitively know? Is it more when it's supposed to be? Okay, so this is all, of course, at the bottom. So how would we do it at the top? What would it look like at the top? Would it be much different?
Notice the other value could possibly.
Well, is the first step still true? This is still true. But that centripetal force, I asked Hannah what direction it was at the bottom. Now it's, yeah, but the 118 is in fact negative. It's down. And that is our net force. And we're solving for the string force, and our weight force is still mass times gravity. And I'm doing a ton of writing here, probably way more than I need to, but for sort of explanatory reasons, I think it makes sense. And the only thing that's different is that 118 on the left is negative. And so when I take that minus 4.9 to the other side, I'm going to have minus 118 plus 4.9, and I get a string tension of
Negative 113.
113.1. And go back to your knowledge statement at the start. Is the string tension less at the top? It sure is. And it's not less because it's negative. The negative just means that it's down. Hard?
No.
No.
I'm waiting for it.
I want to add to this question, find the critical velocity, because we should do a question like that, right? Yeah. And I need to make a mental note to add it myself. What is the critical velocity? V min is the square root RG. Radius here was 1.5. Does the 9.8, should it be negative here? Why not? It's always negative. It won't work because you're going to have to take the square root of negative, right? Yeah, so here is a situation where we don't care about the vector version of gravity because we don't really care about the direction here, right? I don't actually have this number because I've never worked it out.
Yeah, 3.83.
3.83? And you took the square root of that?
Yeah.
Okay. 3.83, and that would be meters per second. Now, how fast were we going here? Oh, 12, so 18.8. So we were going way faster than we needed to. Okay. Yay. I hope this makes sense. I mean, in my notes, I've just called it T, tension. Did you get a centripetal force of 5 newtons?
Yep.
Okay. I don't think you have to find the period, do you?
Well, good to have.
Fw is equal to mg. This is probably a better way to do it, like to do this. Right, so this is going to be minus 2.45, right?
Did you get the thing? No, I used 2.5.
So at the top, it would be minus 5. .55 newtons at the top. And I guess at the bottom, it would just be basically the same, right? It would be 5 is equal to t minus, sorry, yeah, 5. Here? Here? 8. The radius is 8, is it not? 0.8. 7.45 newtons at the bottom. See, easy stuff, right? You guys can do this.
I'm waiting for the.
For the other shoe to drop? The other chestnut? They're really...
Just rolls off tongue, eh?
Yeah. Can't help myself.
Yeah.
I'll take that as a compliment. If you had to find the critical velocity, then I guess it would be... Oh, do we know the radius?
Yeah, 20.
Oh, yeah. And what'd you get here? 2.8? Okay.
Oh, yeah.
Easy. Okay, if you want textbook questions, there are some on page 226, numbers 15 to 25. The only thing where they get a little bit harder is where they ask you to figure out the acceleration in G's. Yeah. Well, I kind of have already, right? If you get an acceleration of 60 meters per second squared, what is that in G's? Divided by 9.8. So in this case here, it'd be like 5.8 G's. Okay? So G's is, I guess, a unit of acceleration. All that's left is to talk about unbanked and banked curves.
This unit's surprisingly easy.
Maybe it's surprisingly easy because of how much you've learned up to now, Hannah.
Because we haven't got to the hard stuff.
All you gotta do is the bank curve stuff.
Is that stuff hard? What's the thing? No, what is it?
A little bit, but like as you're going in a circle around like a circular track and they bank the curve, right?
Yeah,
How would
make
that-
The theory, the concepts behind it are kind of challenging, but like as always, once you get boiled down to the formula, no problem.
I always tell myself I'm going to study and then you know who's better.